Welcome back, geographers. In my experience, we rarely teach students how to think about data, especially the logistics, like how do we store our data, or what are the best ways to back up my data in case something goes wrong. So today, I'm going to share some recommendations with you that I've learned the hard way in the hopes that you won't make the same mistakes I did. At some point in the future, you'll be working at your job, an internship, a research project, or graduate school, and someone else may have a different way of doing all this. In that case, go with their recommendation. First, let's talk about file structures. Why is how we store our files important? Having good file structure practices makes your life so much easier. For one, it makes it easier for you to find old projects and files. As a graduate student, you may start a project your first year, think you're done, then your advisor asks you to come back 6 months later and update something. You might start panicking because your data was all in your downloads folder and now it's gone. Having a good file structure also makes it easier to back up and share your data. Maybe your boss asks you to share your results with a different agency so they can use your results in their analysis. How are you going to share the project if the files are scattered all over the place? What happens if your laptop is stolen or your hard drive crashes? In that case, keeping all your data well organized makes it easier to back up before disaster strikes. Finally, cleaner workspaces result in easier project management, and whether you realize it or not, all of you will be project managers for each lab assignment this semester, plus your final project. Let's work through a hypothetical situation. Let's say you're hired by the Tennessee Valley Authority and tasked with modeling the suitability of a piece of land owned by a landowner they're working with. You might get a digital elevation model, which you can use with a GIS to model how water flows through a landscape. There might also be a GPS exchange format file of GPS coordinates that a surveyor goes out to collect at different locations in the piece of land. You'll probably have a shapefile of the boundary of the land. There might be a zip file containing data on the vegetation types in the area. Maybe a homeowner gives you a PDF of what they hope to do with the land. And maybe you'll also find online a CSV of rainfall amounts collected at gauges in different points throughout the county, which includes the piece of land. On top of all this, your supervisor might also give you a Word document of the protocols you must follow. Finally, you may decide also to collect high-res images of the area using a drone, which you store as JPEGs and TIFFs. How do we then organize all the files for this project to make our lives easier, whether during initial brainstorming stages, analysis, or afterwards when we have to communicate and present our work back to our supervisor, TVA, and landowner? The idea is that we want a single place where we can keep all of these different files organized and easily retrieve them. There is no single right solution, but at a very high level, you may want to think about organizing your files in this manner, starting with a major project folder. Everything that you will be using or creating goes into this folder. The main project folder could then be broken down into smaller folders based on categorization that you like, such as having a folder for original data, deliverables, and documentation. The original data folder contains just what it says, all the original data. It is here in case anything happens during your project, like if you make a mistake or majorly screw up, such as your GIS projects crashing or any of your file documents getting overwritten. Nothing in this folder should be edited or revised. That way you can always go back to this original data set. Almost every project has some sort of deliverable. You might want to include this folder to store any maps you might make, some stored as PDFs and some as JPEGs, or a final report. It is always a good idea to document your work. This folder can include Word documents about the protocol you need to follow, such as the types of analysis for the project and/or relevant quality standards. You can also include a list of all the sources of data you use for your project, just like you do for a research paper. Different people may have different file structures that they prefer, and they can vary in their particular details between academia and industry. This is just one example. For this class, we will create a main Geog 311 folder broken down into subfolders for every lab. There are more than 10 labs each semester, so having one folder per lab assignment makes it easier to find your files and keep up with your finished maps and lab reports. You should include a 0 in the naming for labs 1 through 9. This is because the file explorers in computers sort alphanumerically, and lab 11 and lab 12 will come after lab 1 if you don't also include a 0. Doing this will help keep your files sorted more cleanly and easier for yourself. I'll explain in a minute why I don't have any spaces in these folder names. These lab folders could then include the lab assignment document, relevant data, the ArcGIS project documents, the final deliverables such as your lab answers, any maps and graphs, and any other documents. It's really important to start the semester with good data management practices. It can get overwhelming to search for your work and projects if you don't have an organized structure. Having our data in folders well organized makes it easy to back up our work. Some of you may know this from personal experience, but it is easy for technology to go wrong, so it is a good idea to back everything up. Luckily for us, backups have gotten much easier with time. At a minimum, keep your data on your personal computer along with a cloud backup like Google Drive, Microsoft OneDrive, or the T-Storage provided by the university. It's not a bad idea to keep the original data you download in its original format. Plus, having a backup of your original data makes it easy to start over if you make a mistake. Speaking of which, I highly recommend that you keep a document with the source and URLs for your data in case you ever need to go back and find it again or explain where it came from. If we properly back up our projects and data, it won't matter if our roommate spills orange juice on our laptop, if we leave our backpack on top of our car and drive off, or if your hard drive crashes when your roommate knocks your computer off the table. The university provides OneDrive, Google Drive, and T-Storage for you all to store your files. We'll be using T-Storage this semester because it automatically connects to your GIS software. I'll teach you how to use T-Storage later this semester. You should be backing up your other course files in one of the university-provided backup options. If your hard drive crashes, it won't just be your GIS projects that you lose. Let's switch gears. There's some best practices we should follow with naming our files and projects, and then there are some special recommendations unique to GIS software. Some of these best practices are common to all computers, while some are more unique to GIS software. I think it's helpful to include descriptive information in the file name if possible, something that indicates what the file is. For instance, is this file a deliverable? Maybe include that in the name. We don't include any spaces in the file name because it will result in an error in some software, like our GIS software. Some software doesn't like special characters like punctuation marks or dollar symbols in the file name. Best to avoid them except for underscores. I try to always include the date in a file name so that I know when I was working on that project. Plus, I can always have versions of my files with different dates in the file name, so it's easy to go back in time if I made a mistake. But dates are tricky because different countries use different date formats. Here in the US, we use month-month, day-day, year-year format, abbreviated MMDDYY. But other countries use formats like day-day, month-month, year-year, abbreviated DDMMYY. This can be really tricky with a date like 2/11/99. Is that February 11th or November 2nd? To alleviate confusion, I recommend we use the International Organization for Standards, otherwise known as ISO, format of the 4-digit year, 2-digit month, and 2-digit day, abbreviated as year, 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 month, month, day, day. This helps reduce confusion because some months and days only have one digit. January always appears as 01, and the 8th day of the month always appears as 08. Using a 4-digit year is important because some data sets extend beyond a century. For instance, NOAA has been collecting hurricane data since the 1800s. If we use only a 2-digit year, we won't know if that hurricane was from the 1800s, 1900s, or 2000s. Next, let's spend just a few minutes talking about the basics of file types. Most of the time, you only work with single files. For example, a Word document that you submit for lab assignments can contain text and various images, but is only a single file that appears as a .docx file on your computer. In most cases, GIS data isn't that simple. Let's compare regular files versus GIS files. On the right are numerous file types that you are probably familiar with. Each of these file types is a single file. For instance, if you download a PDF document, it contains all the text and images in one single file. In the GIS world, however, things are often more complicated. A very common file type is a shapefile. This is somewhat of a misnomer because a shapefile is always comprised of many other files. What do I mean by that? Well, a shapefile will show up in your computer as a bunch of files that all have the same name, but a different file extension after the period. The file that ends in .shp contains the information about the location of the feature you are trying to map and analyze. For instance, we're going to be exploring some earthquake data this week, and the .shp file contains the latitude and longitude of the epicenter of each earthquake. The file that ends in .dbf is like a spreadsheet that contains all the information about the feature you are mapping. For our earthquake data, that table contains the magnitude of each earthquake, the date and time the earthquake occurred, what state the earthquake occurred in, and much more. The file that ends in .prj contains information on how we tie our data to the surface of the Earth, so we make sure everything lines up properly. We'll talk more about this later this semester. As you can see, the list of the different files that make up a single shapefile is extensive. Why does this even matter? Well, if you ask me to send you a PDF, I just send you a single file attached to an email. When someone says they're going to send you a shapefile, it can be upwards of 10 different files that constitute a shapefile. If someone forgets to send the .shp, .shx, or .dbf files, then your shapefile won't even open. Let's look at an example. This is hail data in the form of a shapefile downloaded from the National Weather Service. When you download a shapefile and look at the file within your File Explorer, you will see something like what is shown in the slide. Notice that each file starts with the same name but ends with a different extension after the period. As a review, the hail.shp file tells us the coordinates for the hailstorm. The hail.dbf file contains the table of information about each hailstorm, like the date and time of the storm, the size of the hail, and the economic damage from the storm. The hail.prj file contains information that tells us how to tie the hailstorms to the Earth's surface. When you send or obtain a shapefile, all these different files have to be packaged together for the data to work properly in a GIS. We'll talk about the easiest way to do that next. Before we leave this slide though, once you get your shapefiles for a GIS project, don't open them up in anything but your GIS software. It is really easy for the files to get messed up and your data to get corrupted and unusable. Do your data manipulation in the GIS software. The most common way to share GIS data is through the use of what are called zip files. This can be sharing data across email or sharing data from a website that you can download. When we share data, we usually package files together into a zip file before sending it off. A zip file is easy to recognize because it has a zipper icon. Zipping reduces the file size when transferring files to other people. It also makes it easier to send entire projects at once, or even all the files that comprise a shapefile at once. We usually have to unzip a zip file before using it. Sometimes this is called uncompressing. There is already software built into your computer for zipping and unzipping files. We'll practice unzipping files this week. As a review, always use good file structures to make finding and organizing your files easier. Always back up your files so you can easily recover from a disaster or a clumsy roommate. Be specific with your file names and don't include any spaces or special characters. The ISO date format of YYYYMMDD is internationally recognized and makes it easy to share data with people around the world. GIS data tends to be comprised of many files instead of a single file like an Excel spreadsheet or a Word document. Zip files are used to easily share GIS data. You usually have to unzip the files before you can use them. Now it's time to practice what you've learned and explore some data.